launch team was ready to go. This is Atlas Mission Control live from Cape Canaveral, making final preparations for liftoff.
Atlas Systems propulsion, go. Hydraulics, go. Pneumatics, go. LO2, go. Vehicle electrical, go. Light termination system, go. Melon utilization, go. Centaur Systems propulsion.
At Cape Canaveral, some long-cherished assumptions about U.S. space technology could very soon be rewritten. For the first time ever, an American rocket is scheduled to blast into space, powered by a Russian rocket engine.
Go. Vehicle electrical, go. Light control, go. PCLS monitor, go. Light termination system, go. Telemetry, go. RF, go. Complex systems instrumentation.
We thought maybe we misunderstood each other. The performance of the engines were probably 10 to 15% higher than what we had in the United States.
Booms, go. Launcher, go. Water, go. Complex electrical, go. Allen monitor vehicle loads, go.
It wasn't the same technology we're used to. It was a paradigm shift in what we were expecting.
LO2, ready. LH2, ready. Vehicle electrical, ready. Light control, ready. Atlas Systems propulsion, ready. Hydraulics, ready. LO2, ready. Vehicle electrical, ready.
This is Atlas Mission Control, S-minus 5, 4, 3, 2.
Behind the doors of this warehouse in a distant part of Russia lie what for 20 years was a closely guarded secret. A cache of rocket engines designed for the most ambitious space project ever to be undertaken by the Soviet Union. Today regarded as some of the finest in the world, the engines use a unique technology developed by Russia at the height of the space race. A technology so ambitious that Western rocket scientists thought it impossible to master.
The Russians were very secretive at that time, and although they said they were doing something, they did not tell us what they were doing, and in fact it took a great deal of intelligence gathering to really understand what their direction was. The really important things were having good, clear pictures of what they were building.
In the 1960s, the spy satellites of the CIA were keeping regular watch on the Soviets' vast space launch complex, the Baikonur Cosmodrome in Kazakhstan.
In March, April '63, we saw at least some initial what would be called stakes in the grounds for surveyors and stuff like that in the area that was undeveloped on the Baikonur Cosmodrome. The size of the assembly building, the causeway had all the earmarks for a very large launch vehicle indeed. It was like, hello, what's going on here?
The satellite images clearly showed the construction of a new causeway leading up to two huge launch pads side by side. To the CIA analysts back in Washington, the launch pads were the first hard evidence that preparations were underway for the assembly of a huge new rocket. The sheer size of the complex could mean one thing only. The United States was now in a race to the moon.
In the beginning of the 60s, the Russians were far ahead of us. They had better rocket engines, so with that rocket power, they were able to do lots of things that we were simply unable to do. It was a wonderful period for them. First ICBM in August of '57, Sputnik 1 in October of 1957, And then, first man in space, first woman in space, first 3 men in space, first extravehicular activity, first spacecraft to hit the moon.
Russia's achievements in space were down to a unique approach to rocket design, pioneered by one central figure. The anonymous chief designer, Sergei Pavlovich Korolyov, head of OKB-1, Experimental Design Bureau No. 1, and Russia's most senior rocket scientist.
He was very much the dominant figure in the Russian space program. There's simply no counterpart, for example, in the U.S. program. He had responsibility not only for the beginning years, the Sputniks, the manned program, communication satellites, spy satellites, planetary spacecraft. There's no American who had that kind of responsibility. You'd have to equate his work with 15 aerospace companies and about 4 or 5 NASA centers. Very, very much the dominant figure.
His identity a state secret. As chief designer, Korolyov was the most powerful figure in the elite core of the Soviet Space Design Bureau, reporting directly to the Kremlin. Korolyov was the key figure behind Russia's unique approach to rocket design, a pragmatic, hardware-based philosophy in which important design questions were only resolved after full test flights.
In a lot of respects, they were well ahead of the game, but the reason they were well ahead of the game is because they had actually put all the hardware together and had applied that technology far better than we had.
The conquest of space a political priority, Russia's breakthroughs had come through a hands-on approach in which rockets had been built, flown, and improved. And if there were explosions on the way, that was something to be learnt from. From his headquarters at OKB-1 in the suburbs of Moscow, Korolyov started work on a manned lunar mission, with that same experimental, hardware-based design philosophy. But the sheer challenge of getting a man on the moon was a problem on an altogether different scale from anything they had previously undertaken. With the United States already enjoying a head start from their declared goal of landing a man on the moon by the end of the 1960s, the odds against Russia winning were beginning to stack up.
На Луну. Одного космонавта.
As Korolyov's deputy, Vasily Mishin had started working on rockets at OKB-1 after World War II. From the Earth's gravity and the Moon's distance, they soon worked out a lunar mission would need a huge new rocket.
In order not just to get to the Moon, but to land on the Moon, and to bring back an expedition consisting of at least one person, for that you need to put 100 tons into the Earth's orbit. And that means you need to have a rocket which has a starting weight in the region of 2,000 tons.
To build a rocket of the size needed